So years ago, John Gopel and I gave a talk about reading assembly, and the slides for the introduction were actually on either Jason or somebody else's computer, and we we managed to get up and change the title of the meetup from C++ to assembly. So just kind of continuing that joke here. But we are going to talk about JavaScript at least a little bit tonight, and I want to run like a reduce function on the crowd here. So how many people feel like they know enough HTML, JavaScript that you're going to understand this talk pretty well? Okay. How many people feel like they could go out and be a JavaScript developer in the market today? Okay. How many people know about WebAssembly? Does anybody actually use WebAssembly for their job or done so professionally before? Okay, we're down to one. And Emscripten? Yes? Yeah, okay, wow, cool. So we've got one. So yeah, this talk is about targeting WebAssembly with C++ through Emscripten. I'm Anthony Scimone. You can call me Tony. Most people do. And yeah, we're really going to be talking about the relationship between accessing C++ code in the browser through WebAssembly, and we do that through a tool called Emscripten. So what is WebAssembly? So WebAssembly is a binary instruction format for stack-based virtual machine, and it's designed as a portable compilation target for programming languages. It was introduced in 2017. This is a quote from the wiki page here. The main goal of WebAssembly is to enable high-performance applications on web pages. Just a few facts here. The extension type for a binary is a .wasm, and the extension type for WebAssembly text files is a .wat. We'll get into that a bunch. But what does this have to do with anything? So Emscripten is an open source compiler toolchain for targeting WebAssembly for browsers, Node.js, anything that does WASM runtime. And it can be done for C, C++, or any language that uses LLVM. It is essentially the Clang front end with the LLVM WebAssembly backend. So it can do all kinds of stuff. You can convert OpenGL to WebGL. You can use a tool called mbind to facilitate binding C++ functions to JavaScript, and it provides a number of libraries to help you with additional operations. We'll talk a ton about that too. So why would you do this though? This is a question I find myself asking all the time. I now work on a WebAssembly project at work, and that's really how I got into this, and that's kind of what brings you this talk. So back in April, we inherited a code base that is C++, ported to WebAssembly. And it actually uses a pretty interesting paradigm there where it runs C++ on the front end and the back end. And so really that's for code reuse, which is a really great reason to use WebAssembly. Maybe you have existing code or you have some sort of historical reason for using WebAssembly. I think that's probably the most common for using Emscripten specifically, sorry. You've got something like image processing software that was written in C++ ages ago, and it works, and you're not about to change it, you just want to port it to the web. Emscripten is a great tool for that. You want to use Emscripten for performance reasons. There are definitely situations where WebAssembly can be very performant and really speed up your web pages. And so that might be one reason that you would use C++ through Emscripten to get to WebAssembly. You could also just be, you will only write C++ because you love to suffer in that way. And now you're a front-end engineer because you have Emscripten. Totally viable as well. So I'm not going to make any, we're not going to talk about performance here tonight for any examples or anything that I do here, but I just wanted to make a note about WebAssembly and performance. When I was preparing for this talk, I read a ton of blog posts about performance, and at one time I kind of dreamed about making this talk about making performant WebAssembly better than JavaScript. That's the real reason that you would do this, and it is a reason. But talking about performance with WebAssembly, especially for something like using Emscripten to get to WebAssembly over JavaScript, it's really hard to make claims about performance with this kind of thing. It depends on a lot of factors. So, I mean, WASM is strongly typed, so you gain a lot of advantages there. It can pretty quickly be turned into machine code by the browser. But, you know, compilers for this thing are still in their infancy and gaining a lot of traction and stuff. And I have seen a lot of instances where compiled JavaScript actually outperforms the compiled WebAssembly. And there's this other aspect of this where accessing a WASM module has a cost. And so if you're just writing a really simple example, like the ones we're going to see tonight, and you're going to go benchmark them, it becomes really hard to write some sort of benchmarking framework around this to abstract out the cost of actually loading up and accessing the WebAssembly module versus your JavaScript, which is just kind of already there. If you're running things on the back end, things get even more complicated because WebAssembly doesn't really have a warm-up period like compiling JavaScript does. And so things become even more murky when you try to do that. So if you're thinking to yourself, I want to use Emscripten C++ for WebAssembly because it's fast, you really have to be careful about that. And golden rule, you need to just benchmark the whole loading of the whole thing because it becomes very difficult to abstract away the part that you care about. So enough talk. I want code. Oh, so let's take a look at what assembly code kind of looks like. So handy friend, Compiler Explorer, it's great. You probably can't read this, it's so small. Is that right? Yeah. Yeah, I should have preloaded this. Give me 20. How's that? Better? Yeah, really simple function. I want to cube something. And our assembly code looks not that different from the kind of assembly code that we're used to seeing. I don't find this kind of assembly really easy or useful for WebAssembly specifically. And we'll get further into a format that is a little bit easier to understand and a little bit easier to use when you're trying to debug some sort of problem with your WebAssembly. But yeah, you can see here, I mean, get the same flags, right? It's just like compiling normal C++ for the most part. It's using Clang front end for all extents and purposes. It's a very familiar process so long as you have Emscripten set up. It is, yes. I think that was on the first slide. Like that's WebAssembly. You're good. WebAssembly is like 4 stack-based virtual machines. Back to slides. So I want to talk a little bit about Emscripten itself before we get into WebAssembly, because Emscripten will do a couple of things for you that are really helpful, and I just want these things to be out there before we start getting into examples and I start compiling things with Emscripten and everybody's like, slow down. So Emscripten will sort of take an operation based on the output that you give it. So if you ask it for a WASM, it's going to give you a WASM. And the way you indicate that is by asking for a .wasm in your -o, right? Like the output of this compilation is a WASM. It's going to give you a WASM. It expects a main in that case, or if you're just exporting something like a library, then you do it as a side module. We'll get further into modules in a minute. If you're asking for a JavaScript file, what it's going to give you is a WASM with a JavaScript file that really has all the boilerplate set up to load that WASM. And you can just call that JavaScript file from your HTML page, and it works like a charm. And if you ask for an HTML, you get a WASM, you get a JavaScript, and you get a really not so helpful HTML file for looking at things. We're going to see them. You don't ever do this unless it's like your first day doing Emscripten for the most part. But it is most of our first day doing Emscripten, so we'll do it. In order to sort of have a holistic approach to this, we need to know some things about WebAssembly in general. So when you're accessing WebAssembly from JavaScript, you have this really useful JavaScript interface. And we affectionately call this the JS API. And so everything is kind of hidden behind this WebAssembly namespace. I actually don't know the right JavaScript word for what this is. I probably got it written here. yeah, I guess it's just an object, right? So your WebAssembly module, trait on that object, which is a different object, is essentially all of the stateless WebAssembly code that's been compiled for the browser. If you've accessed a WASM and your WebAssembly has a .module, you've got WebAssembly code that you can access right there in the browser or in your JavaScript runtime. A WebAssembly instance is basically a module with state. It's actually using a memory buffer. And then the WebAssembly.memory object, which will become important if you're ever really getting into these things, but I'm going to try and leave details about this out for this talk as much as I can because it becomes sort of complicated. I mean, that's basically all of the memory that your WASM has, including like your functions live in that memory, your arrays live in that memory, anything that you declare, it lives in that memory. Well, there's one more slide about that we'll talk about just to give you some basics, but this is what we've got for a JavaScript API. So I want to talk about modules because it's basically our fundamental unit of WebAssembly is that WebAssembly.module. And this is kind of what it's not kind of what it looks like. This is what it looks like. And so modules are represented as a large S expression. And some of you guys who are more familiar with Lisp might know about S expressions. It's basically a way to textually represent a tree. And that's how WebAssembly organizes itself. But WebAssembly is mostly a very flat tree. And so everything is contained inside of this module here. And you can see it declares a whole bunch of stuff. I've got an export for an add function. I declare an add function. I've got some params. I've got a result. I've got some logic. I've got a memory object. I've got a table. Everything that you need for this WASM is inside of the module. Functions themselves, and I'm sorry, hold on. The other thing that I really ought to say here is this is WebAssembly text format, right? WebAssembly is a proper binary. If I try to open a .wasm file, I get gobbledygook, right? You have to convert any WASM binary to WebAssembly text if you want something that's easy to read that you can actually kind of understand. It's basically the same equivalent as if you had binary code and you want something like assembly, like it's just not readable until you get back to that phase, right? So yeah, functions in WebAssembly text look like this. You get a function, you get a signature. That's the name or reference of the function. You've got your locals. That's basically your params for this purpose. Those get initialized to whatever value the caller calls with those arguments. And then you've got the body itself. Any local that's marked as param is a parameter for that function. And then there is usually a local marked result. And that's the result for that function. And then we have the WebAssembly.memory object. Like I said before, it's a buffer. It's a resizable array buffer, or it can also be a shared array buffer if you're trying to do some multi-threading web worker stuff. And so the default value that you're going to get if you ask Emscripten for nothing is 16 megabytes. And if whatever you're doing takes more than that, you're going to crash. And the maximum that you can actually allocate with Emscripten, I think this might be WebAssembly in general at the moment. I don't think that you can really get more than 4 megabytes. With Emscripten, I am pretty confident that we just got to that level in 2020 to pass a flag to get up to 4 gigabytes. If you're thinking about the context of a web page that has things that are loading WASM, and that WASM alone is 4 gigabytes, if you're getting to that point, your website is huge, right? And I hope that you're like mining Bitcoin on their browser or something, because like that is a lot of memory. This is the process of turning like C++ code into WebAssembly text, right? If I have something like this, cube function takes an int, returns that int cubed. That's going to look something like this, right? Func cube param, I've got an i32 int, and result i32 int, and I'm going to grab my local 0, that's that param i32, and I'm going to grab it again, I'm going to multiply those together, I'm going to grab it a third time, I'm going to multiply it, And if you're familiar with Rust, or I think there's a bunch of languages that do this, the last expression on the S expression, that is the function, is what it's going to return, right? And that does need to match the return type. So that's what that looks like. So don't take it from me. Let's actually take a look at that. So I've got here, can we see that okay? Yeah, that looks okay. So I've got here a main file, right? Oh, this is bad. This is from me toying earlier. Disclaimer, this is not like going to be an all slides kind of talk. I'm gonna jump in here and do a lot of examples and a lot of live coding. And I figure that that's a lot more useful than just talking about this stuff, is to actually see how it works and play with it. So if I go into this example here, and I make, you can see, what was that? Do we have a question somewhere? Okay, I'm going to pretend it didn't happen. Yeah, no worries. So this is some pretty familiar syntax, right? This is just compiling this C++ file through a make file with Emscripten. I call em++. I give it an optimization flag. I ask it for WASM. I give it a side module because this doesn't have a main. Remember, I said something about that earlier. And I want a WASM file as my output, right? And it actually went into my build. I don't know what this other one is. And I'm going to call, I have an executable here for the WebAssembly binary toolkit, just stuck into this file. We don't need to know much more about it than that. And I want a watt of this thing. So here you are, this code, cube, turned into this. It's not exactly what we saw on my slide. I, wrote it like you would write a WebAssembly function by hand. But it's really close. We can see this func1 here is exactly that thing, right? This type 1 here always confuses me. I think it's because we export this function, and so somehow this thing is of type function. This is a question that I still have about WebAssembly, if anybody can answer this. But for debugging the function itself, this is pretty readable, and this is how you would, I guess, just read your WASM binary if you're trying to debug through it. And it gives us a sense for what's really going on here. How does WebAssembly work in the browser? Demonstrates that it's strongly typed, et cetera, et cetera. So that gets us some places, but the step from getting to here to doing something in the browser still feels really far away, right? Well, thankfully, Emscripten gives us a ton of utilities. I'm not going to go through all of them, and we're not even hardly going to touch the surface of the kinds of functionality that are in all of these things, but wanted to make you guys aware of a few of these that are really essential for working with WebAssembly with Emscripten in C++. Emscripten.h is a header file that has a ton of functionality in it for using JavaScript and compiler directives and all sorts of things inside of your C++ code itself. HTML5.h, same kind of thing, but for HTML functionality. I have never used that in my life, but it's there. Preamble.js, programmatic access for interacting with compiled code in JavaScript. Has a lot of useful stuff in there if you're really needing to do complicated things in your JavaScript runtime itself. Ccall is a really good example that actually lets you wrap around functions if you're needing to pass complicated arguments from your JavaScript to your C++ functions. Just calling them straight up might become more complicated than using ccall and then passing arguments with it. Val.h is really cool. This is support for representing any JavaScript object inside of your C++ itself, and there are tons more. Let's just look at them real quick. So you can see here's the API reference for Emscripten. There's tons and tons of of files with all sorts of useful stuff. So most likely if you're trying to do something in C++ for interacting with JavaScript or some sort of web technology or a runtime or something, there's probably a helpful library in here for you. Okay, how am I on time? So it's time for examples. Live coding, much fun. So let's get rid of wasm to wat. We don't really need that anymore. Let's call C++ from JavaScript. So I've got a hello world here. And I am needlessly guaranteeing that I have C++ 20, because for some reason I was like, they need to know it works. Is it pretty hard to see? Well, is that easy to see? Okay, hold on. Okay, this is my hello meetup. Okay, and so same thing here. I've got a make file. I'm going to make with my 20 standard. And you notice instead of asking for a wasm this time, I asked for a .js file. So I can actually call node on that .js file. Whoop. And I get hello CPP meetup. What's happening here is that it's actually finding the main and saying to JavaScript, the main function needs to be run the minute you call this thing. Right? But I am also doing something else kind of interesting here, where I've got mscripton.h included, and I have this mscripton keep alive command on a different hello world function, right? And so if I do this same thing, well, let's modify the make file, and let's ask for an HTML. And this time, actually, I want to talk about this first. Notice that my JavaScript here is really, really readable, and just a giant wall of boilerplate text for getting mscripton running. If I'm not mistaken, if I pump the compiler flag up, it's actually going to minimize that for me. And I want an HTML. Now I'm going to make. And so in my hello.js, yes, it's actually done work to optimize the JavaScript as well, which is pretty interesting and very helpful. And I've got this hello.html file. If I try to open this right now, I'm going to get cross-origin errors, which is something I know one very silly way around, which is to just run a Python server. And now, if I go to localhost 8000, I'm just serving this directory. The delay here, I can't handle it. And I ask for hello.html. It gives me like this text box with what that was doing. Again, we've seen the HTML functionality. We'll like never do this again. But in the console, I have my, yeah, is there a way to blow this up? Aha. WebAssembly.module. What do I call it? How does this work? Oh, it's just the module. Well, I knew something like this would happen with live coding. Am I in the right file? Do I have the right example up? It says 2. I have an mscripton keep alive. I'm asking for a hello.html. And am I clicking the right hello HTML? Oh, can't see my web page. Where do I output it? That's what I need to be asking myself. My make file. I do output it to build. Should be the right one. Hello CPP meetup. That's right. That should work. We'll see it on the next example either way. I'm not sure what I did wrong here. I went through this like 3 times today. Let's just try the other. Well, I bet you I can get it with ccall. There it is. Ccall to the rescue. Hello, CPP meetup. And so if I try to do the module itself, I have hello world. It is there. Hello, CPP meetup. This is essentially what I was trying to get at, right? So my main function is calling one function. It prints out hello, CPP meetup. I put mscript and keep alive on this other function. And what that told Clang is, you don't see this code anywhere, so you're going to kill it, but I'm going to use it in the browser. So don't kill it, and I want you to automatically export it. So this was a separate function. It prints out the same thing, which is confusing. I probably should have not made them print the same thing for clarity's sake. But you can see now kind of the utility that something like mscriptin.h offers you. These functions for doing all of these different kinds of operations to really make what you're trying to do with your C++ code and make it portable to the web easy on you. And also how it's really easy to get to functions and use them inside of JavaScript itself. Does everybody here understand enough JavaScript to understand what's happening in this? This is the console. I can just type JavaScript in here. That's all very apparent, right? Okay, cool. Yeah, so I guess we kind of just did this example, the mscript and keep alive. We'll look at the code real quick, but it's essentially the same thing. I think it's like a DLL export. Yeah. Sure, I'm over here on my Mac like, what? So Clang, if I try to compile this with Clang, right, it sees hello world here, right? And it says, you're not using this anywhere. Like, I see main, I know everything you're doing. And I'm Clang, I'm going to optimize the daylights out of this. Yes. Yeah, and so this, I mean, it does exactly what it says once you understand the context. It's saying like, keep this alive. Don't delete this code. This needs to be exported. It automatically exports it for you too, which is really helpful. And so the final example that I wanted to talk about for, I'm not sure. Let's find out. He asked, if I turn off the optimizer, does it still go away? And I said, I'm not actually sure. Well, I don't have the optimizer on, so that makes that easy. So I just get rid of that. And then I should be able to reload this. I just get scared that there's like some caching issue going on here in the browser. I don't appear to have it anymore, so looks like it. There you have it. One more operation I want to walk through, just as a quick example, is we've seen C++ code in the browser now. That's pretty easy for our small toy examples. Build processes and things is where this starts to really bite you. I specifically am not doing any CMake here. But I want to talk about calling JavaScript from C++ itself. So I've got a main.cpp file here, and I've got Emscripten, and it gives me the ability to do this emjs, where I'm basically getting a call for mbind to bind some JavaScript to my C++. And I'm just going to console log something here. So if this works, we're going to see that string going from our C++. You see I'm calling the function console log here in get double number. That's sort of the way that emjs works, is I need a return type, function name, and then my parameters, and then I just write JavaScript. And so I ask for a main, and I have a JavaScript file here. And this is another point I wanted to demonstrate is, we're done asking for HTML files. We can just HTML file, call that main.js, and it works beautifully. And so let's go back to my file browser here. JavaScript, but it doesn't look like it called it, does it? It doesn't look like it. Where did my make file port things? Get double number. Oh, I need to call get double number. I'm really smart. Houston, we've got JavaScript in C++. So there you go. So this has been our foray into getting to WebAssembly, inside of JavaScript with C++ through compiling with Emscripten. I want to stop here and take questions. Where are you guys at? What makes sense? What doesn't make sense? Yeah. This is all pretty. I think this is all pretty basic stuff, really. So. Oh, I love this.
From the JavaScript in C++, could you call back into C++ or into C++?
Absolutely.
And then can you bounce back and forth infinitely?
Absolutely. Yeah. Something I didn't talk about before that's been on all of these examples that I feel really bad for missing. This is what I get for looking at this and not notes. So everything that you export, other than main, your main functions will work just fine as they are, but everything that you export in C++ has to be externed as C to avoid namespace mingling. Emscripten just won't really deal with not doing that. I've seen, they have some stuff on their docs about, you can get around this by doing this, but it doesn't work out all that well. So really, if you're going to be exporting functions, exporting a library, doing something like that, you need to extern everything as a C function, which in our live coding example that we'll do here in a minute, that poses some challenges for us, as I'm sure everyone can kind of imagine. I can't return something like a std unique pointer. Brian, do you have a question?
Yeah, what kind of tech do you use to call back and forth functions? If you're calling to the
I'm guessing it just wouldn't compile.
Well, no, but you expect to do the console.
Oh.
Oh yeah, of course, I is 0.
Yeah. What's up?
I didn't see your double code, but I'm wondering, like, would it be okay if you were like take the input and then add it to itself? That way you get like high plus high, and then does that work?
I think what you're asking, the question, everybody can hear him, he's got the mic. So I think you're asking, what if I did module dot underscore get double, something like this? Is that what you're asking?
No, if you went back to your JavaScript, I didn't see your, I don't remember what your
Okay, let's just pull that up real quick.
Or like, are we limited because, because we typed it there?
Yeah, it's strongly typed on the EMJS side.
Okay, yeah, I was wondering if instead of x times 2, you said x plus x, that would work, but since it's strongly typed here, probably not.
Yeah, I don't think so, no. That you should get a compiler. Ben. Oh, I'm sorry, I did not see that.
So the professional JavaScript programmers I know tell me that no one writes JavaScript anymore, they write TypeScript. So have you tried this with TypeScript, and does that improve the strong typing at all?
I haven't tried this with TypeScript itself. I would imagine that would just work better. Like the loosey-goosiness of JavaScript actually causes a lot of problems here, and WebAssembly is strongly typed, so I don't know, really. I haven't played with that at all, but I imagine that works better than worse.
But that would not work because you need a TypeScript interpreter. And TypeScript is compiled around the network.
Yeah.
Yeah, I'm not really sure. I mean, I know that most people who are messing with WebAssembly for TypeScript would use assembly script, which is a TypeScript-looking language for writing WebAssembly. So I imagine that the interoperability there is a lot stronger.
So assuming a non-trivial program, is there for in the browser where you can step through your C++ like with GDB or whatnot, or are you reduced to throwing in print statements if you're?
No, you can debug through your WASM. Yeah. Huh? Yeah.
Compile symbols,
Line directives.
Yep.
There's a debugger that you can use in JavaScript, and it loads the WebAssembly.
And you can see the C++?
as well. You can see the C++.
Oh, that's awesome.
Okay.
Yeah.
If you pass the string 5, will it print 5?
This is the kind of talk I wanted. I was like, I'm not going to spend a ton of time on slides. It's pointless. They're gonna throw the sink at me. There you go.
So there is comments from Leslie coming in about typing and between Emscriptum and TypeScript. He says, my experience with Emscript and TypeScript is that we need to manually define types. I don't know if there's some kind of reflection to make that automatically happen.
I imagine that Emscripten deals with this problem in some utility that it gives you. Right?
Yeah, he also said they have a C++ wrapper. I forget the name, but it has some limitations. And I think Leslie should just unmute and join the conversation.
Yeah, there you go.
Yeah, the C++ wrapper is called bind.h, so it provides
yeah.
some support to things like state string.
Bind.h. Yeah. There you go. Now, here's a great question that I don't know the answer to. Is it the docs that are under construction or bind.h? Most of what I've had experience doing in C++ WASM is really doing computational things on the back end and the back end, and passing it back to JavaScript and displaying it for the user, right? I mean, this is that's really the pretty typical or common use case. Like these ideas of like going back and forth between C++ and JavaScript, I struggle to find a good use for those. At some point, you should probably just start writing JavaScript. Yeah. So that's it for slides. We can get rid of all of this. And the last thing that I wanted to do is walk through coding up an actual solution. Like let's take a C++ library, and it has no WASM capability at the moment, right? And let's take what it does and run it through Mscripton and export a function and call that on the front end in some way that's useful. Back when I was just getting started with this stuff, I had a coworker named Mike Williams, and he had a little library that he had written for generating Mandelbrot sets. And he used a PNG output tool to, output those pixels to a PNG file and, display his fractals. And I think we can actually see them. Check it out. VS Code, ladies and gentlemen. And so we both took a crack at this, and I really thought that his solution to this problem was just a great example for the purpose of trying to walk through something in 45-ish minutes and do something real. Like, let's create a real WASM example. So I think what we should do is run through that and make it work. So we're gonna just start off and make a WASM folder. And in there, we're gonna make a makefile. And we're gonna give ourselves a makefile. And I'm going to do a lot of copy and pasting here because if I had to hack this whole thing together, we would not make it through this talk. We would go to Burns at like well past when they close, right? So I'm going to simplify this down pretty well. I'm going to give myself a nice compile string here, and I've got the appropriate things to my my libraries that I'm going to need, and I'm going to call this main.cpp. But we're not really going to put a main in here, right? Let's actually call this no, let's not call it Mandelbrot. Let's call it export Mandelbrot, because that's what we're going to do. And so we're also going to need a file, and we're going to call that Mandelbrot. Yeah, why not? I don't think that interferes with any other files in this program. Mandelbrot.cpp. Did I actually spell that right? Is that how you spell Mandelbrot? I think so. And so in order to get through this part, we would just need to know a lot of things about his library, right? So I'm just going to walk through a lot of this for you. How exactly does his library work? We can go to the .exe, Mandelbrot main, and we can kind of see it here, right? How he's done things in the past. I hope that Mike doesn't mind us perusing his library. I think it's a really great example. You can see he takes in some parameters in order to generate Mandelbrot from some viewpoint, right? If you know anything about fractal sets, you have to have some mathematical understanding of what set you're generating, because you can zone in on any specific set and continue to generate more sets. That's how fractals work. And he has this API for setting his shading. And then he has some stuff in here for benchmarking, how long it takes. And then he has some code in here for actually writing out using PNG writer to an output file. And then you can see here, he just goes through and actually sets with this RGB struct the X and Y coordinates in that PNG file and sets some RGB values. So pretty simple, right? So in order to do something like that, we're going to, in our WASM, we're going to export a function. And this is going to return, we don't really know what yet, right? So we're going to return a raw pointer, since this is C, type of that struct, right? A pointer to that struct. And we're just going to call this generate Mandelbrot. I'm actually going to use, see, another point that I forgot to mention is that whenever you export a function in, when you export a function in Emscripten, it automatically gives it an underscore at the front of its name. You might have noticed that I had get number or get double number or whatever I had my function called in my previous examples. And when I called it from my WebAssembly, I typed underscore that, right? I think this is to avoid name mangling inside of JavaScript itself. Yes. Is that a question or a statement? Okay, I thought so.
So it's a JavaScript.
Yeah.
Okay.
And so in order to do this here, to generate a Mandelbrot, I'm going to need some kind of size, right? That's just how this function needs to work. So I'm going to say int size x and int size y. This is the actual size of pixels we're going to generate, right? There's no other way around that part. We're not going to hard code that. And then we need to actually give it some parameters. And so I'm just going to pull this part in because this is just API knowledge. This is how this API expects some of this to work. We've got some params here, and we'll talk a little bit more about how those params work when we actually go down to the function. We're going to steal straight from the other main the exact same code for, this is not pretty. Hold on, my conscience won't let me do this. And I also, we really ought to be word wrapping, shouldn't we? So that we can really see. Yeah, I'm basically setting here that I want my RGB shading to be black and white. It's just the way his API works. You can see that from the inset color and the out of set color that he's just like setting black and white. I think that's right? 255 is black and 0 is white. Does anybody know that from, is that flipped? Yeah, okay. Been a long time since I was a front-end engineer or did any front-end work or anything. And so then we're going to make a call to his compute function, compute Mandelbrot, give it my params, black to white, and I get a result. And so now we start to run into some kind of trouble with how are we going to get this thing to our WASM. And the way that we're going to handle that is we're just going to use a global pointer. And this is really kind of okay because remember we have a memory buffer and everything that we do inside of our JavaScript lives in that memory buffer. And so long as this code is running on the front end, which I'm going to make a strong assumption about this here. And if we were really needing to do memory management inside of like a long running WASM, or I mean a long running, Node.js environment, then I think I would need longer than I've got right now to set that up and figure that out and think about it. So we're just going to have a global object here. We'll call it global RGB. We'll make that null pointer. And what we're going to do, question, sorry? Thank you. I'm going to allocate. Is that how I did that before? Spaces are good. Size X, size Y. Yep, okay. And then real simple, I'm just going to run through the whole thing. Is that right? I don't have params anymore. I do have params. Yep, I do. Size, we'll make this size y, and plus y, and for int x 0, x is less than params dot size x plus x. What did I call this thing? RGB result. I need an index. And then I can actually just start setting these things. I'm just going to grab this code here. And finally, am I still inside the right function here? I'm going to return my global RGB. And one thing that I am going to do here is actually delete whenever I start this function up, right? Anything that's in global RGB. That way, if we start calling this function multiple times, we at least don't blow out of our memory buffer inside of our JavaScript. So this was the, I don't know, like this was the part of this where you just had to have some knowledge of how his library works. And the C++ code here is really straightforward, right? We've got 33 lines of it. We've got a pointer. It's to a struct, and that RGB struct is just our RGB, right? Values for what our colors are. And so we just go through and fill a flat array with all the values that we're going to need. It's really, non-structured, but that's what we're going to have to do in order to deal with it in our JavaScript, right? So we've exported this. So can we get this thing in our JavaScript? Let's find out. So I've got my make file. No. Where is this? This is. Yeah, this is where we're at. I have a make file. I didn't put all at the top. CPP, export Mandelbrot. No file or directory. I called it Mandelbrot, and then I called it export Mandelbrot here. What's that? No, I don't think so. I think I just called it the wrong thing. Right? Undefined simplified Mandelbrot. I think I'm in the wrong directory here. I must be. I named my function generate, and I tried to export simple. Oh, you're right. Yeah. Export. Yeah. Need an underscore. I'm not in the right directory anymore. Cool, I have a JavaScript file. So now let's make an HTML page and see what we've got here. Index.html. And I'm just gonna steal some HTML here. And nope. I don't need anything more than to finish the body, right? I need to finish the body. I need to finish the HTML tag. Okay, cool. And I'm going to call a script. And I barely even remember how this works. This is how much JavaScript I do. I say something like this. And what did I call my WASM? Mandelbrot.js. Okay, back to localhost. Let's put at least something on this file that we can see. So inside the body here, doesn't this go in the body? This goes in the body. Cool. Cool. Our console. And if this worked, I should have generate Mandelbrot. And this is going to take something like, what's the size of a screen? 1920 by 1080? 20? We got a great error here. What do you guys think happened? Ran out of memory. Mandelbrot set is bigger than 16 megabytes, which is what we got by default, right? So we can go back to our, wherever this junk is. No. Back to our make file. And we can give it more memory. We looked at that before. So I'm just going to give it 100 megabytes. Is this overkill? I don't really know. But it works. Dash S, total memory equal 100 megabytes. Let's see now. Cool. We got a number. That's super helpful. So what this is essentially a location inside of our array buffer, right? You can think about it like we got the address of a pointer, essentially. This is just the front-end format of that. This is like a location inside of our memory object. So real helpful. How are we going to deal with that? Remember, what we've returned back to this is essentially a flat array of numbers where it's going to have an X, a Y, and an R and a G and a B. I think that's how it actually might just be R's, G's, and B's. And so in order to actually put this onto the screen, we're going to need to do quite a bit of JavaScript. And this is the part of this that's really fun. So let's go back to our code. And let's go back to our index. And let's start employing some JavaScript techniques that I used in the past a long time ago and understand not that well anymore. One thing that anybody who knows a lot about JS here will know is that whenever you're trying to draw something on the screen really frequently, we make a canvas element. So we're going to do the same thing here. And then inside of our script, we're going to grab the canvas and we're going to grab the context of that canvas. So I've loaded up my WASM module, and then I'm going to make another script. And I'm going to grab the canvas and then the context of that canvas. Great, I've got a thing. I can supposedly access that somehow. Well, we're going to need some kind of function to draw this thing, right? So we're going to say const draw Mandelbrot. And we're going to make this an fat arrow function because I like them. And so we need to do something with that data, right? Well, JavaScript gives us a pretty helpful way of dealing with that with these I32 arrays. Come on, give me an, yeah, there we go. And so what I'm going to give this thing is I'm going to give it my, where does that get declared? It's an actual thing. WASM memory.buffer. I would have expected this to be like the actual capitalized thing, but I guess we can access it that way. I'm going to give it my buffer. I'm going to give it my function. What's my function called? I'm going to do exactly that. Actually, instead, what I'm going to do is say canvas dot width and canvas dot height. That's more better. My canvas width and height is the right size of a screen. And then the last thing that I'm going to do is give it like the actual offset here. Oop. So width times canvas dot height times 3, because that's how many elements we've got for each thing. And now, what's that? Love it. You can also see how I got out of the habit of putting semicolons on things from sitting here messing with this, because JavaScript is loosey-goosey. Let's call that pixels, and let's see what we got here. No, I don't want that. I want draw Mandelbrot. Did I give it params? Or did I just hard code the whole thing? Hard coded. Now I've got an enormous array of stuff. Great, I've got my data from WASM. It's here in the browser. Now I have to be a front-end engineer. This is normally where I stop, right? And I think most people in this room are probably in that same situation, where like delivering this kind of data is the real point of this kind of thing. But that would be no fun. We're definitely going to draw the fractal. So in order to draw the fractal, that's really easy. I can basically just use a function for drawing each pixel, right? We're for loop through the width, for loop through the height. We're going to splice the section of the next section of our array into a segment of 3 to get the R, the G, and the B. And then we're basically just going to draw it onto the canvas. That's should be it. One thing that I am going to get rid of is this hello, because I'm not sure where that's going to go. See, I'm not real good with CSS. Yes. That's it. That's the end of my talk. Big shout out to Mike Williams for having this code and also doing a lot of the solution that I presented to you tonight is code that I borrowed from him. Who's got questions, or are we ready to go to Burns?
Well, I'll go ahead and I just realized that I didn't actually say anything about the burns during the intro.
Oh yeah, time for Burns.
So I should probably say something about it and then you can take questions. So
okay, go for it.
after my announcement here, we go to this pub, it's called Burns, it's right over here, it's a crazy little weird British pub. Anyone wants to come, all races paying for the
First 2 drinks, no food.
first 2 drinks. And theoretically, someone already called ahead, but we haven't
Chat.
as many people actually here at 6 o'clock as there are now.
Chadwick called, we blame him.
Okay, but yeah, so Burns Pub, if you want to have drinks or you don't have to drink. Anyhow, 2 questions. Oh, and take care of your own trash when you stand up. The trash cans are recycled.
Please.
You, is this on? Okay. You allocated inside your C++, and then just return that pointer out, and it points to somewhere in your giant data buffer for your browser.
Exactly right.
Okay.
Yeah.
If you had a C API of functions where your functions return a raw pointer or any pointer that you allocated, obviously a global is probably not the best move there.
No.
Yeah. How are you? It's kind of painful when you have a C API that returns a pointer to memory you allocated,
Yeah.
and then someone writing JavaScript has to go back and call the JavaScript function that frees that memory.
Uh-huh.
Are there tools with this to make that less painful?
There probably are. I haven't really gone super far into that. I debated like trying to make something that was really memory efficient for this talk. And as I started to play with that, I realized that even the process of explaining it would take longer than we really want here. I'm guessing that Mscripton does have some utilities for you there, but I don't really know. Relying on my front-end engineer to call some sort of clear function that I give them is, I mean, essentially they have the WASM buffer on the front end here, and they kind of have to manage it. So that's the way I've always seen it. Not sure.
It's possible that allocate the array of JavaScript and pass it to C to avoid the copy, but it's more painful than the current approach.
Yeah, that sounds about right. I mean, the other thing that you could do here, which I didn't do because it's not, it's just more coding, is we could generate the Mandelbrot in like sets, right? And deliver it to the front end in smaller increments. And so, you know, I could have, with more coding, delivered each set of RGB and just ran through a loop on the front end and got them all, right? We'd have to do, like, his API doesn't want to do that because it wants to compute the Mandelbrot right then and there, right? But it takes all these params. It's totally, you know, doable. And then what? I've got a struct of three ints, like, you know, that seems like a pretty reasonable approach as well.
Hey, thanks for the talk. What options are there for building code that works with Mscripton, but also can be compiled to your host OS as a native program?
I mean, we do that with CMake.
But like any like particular things? I noticed you had the Mscripton header in your code. Do you just have like preprocessor magic that's driven by add compile definitions that disables that?
So, I mean, like anywhere that we have code that's really Emscripten specific, then yes, we preprocessor that. But you can get away with most of it by separating out your executables. You have some set of code that compiles to a WASM. You have some set of code that compiles to a C++ binary. And you can normally abstract all the shared layers out to some sort of set of libraries. And if you find that you've got Emscripten specific code in there, then yeah, my best advice for you is to start if-defing. John?
Do you have any sense for how widely used Emscripten is?
No. I'm relying on it not be to give this talk.
Maybe follow on to that. Do you have like a really cool website that does something awesome with Emscripten?
Ultrix
Yours?
Cloud
Or,
does.
yeah.
Yeah.
Do you want to show us yours?
Yeah, Ultrix Cloud uses WASM, and the Ultrix Cloud powered by Trifacta front end. If you're, I'm not a very good Ultrix Cloud user, but I mean that's the product that I deliver, and so it basically allows for downsampling and configuration of your workflow in the browser, so that you can actually walk through your whole design time before kicking it off to the backend.
Well, this is your kind of thing. All of the DOS things on archive.org run through a Emscripten compiled DOS prompts. You can use
There you go.
The big one is Figma. If anyone's used Figma, it's a tool for making like diagrams and stuff in the web. And that is not entirely, but very largely built in C++ with Emscripten.
I got another one for you. They're not here tonight, but sometimes two guys from SketchUp come.
They just messaged that on the discussion.
Oh, really? Oh man,
You can't see.
if
SketchUp.com.
they probably like painfully kept themselves muted through this talk. So SketchUp is a 3D modeling program that runs in the browser. I'm pretty sure that's what they do there too. They might be able to. Can you tell us?
Yeah. Sorry, I really wanted to be there, but yeah, I worked on this stuff. We ported 500,000 lines of code to the web using Emscripten.
There you are. Really? Nice. There you go.
Sean Parent worked for some years on making it work because it's all multi-threaded code, and this code can't be multi-threaded. So
interesting.
He has a presentation about it from, I don't remember which conference, but you can probably find it online.
Multi-threading in WASM is a really interesting conversation. There's like multiple approaches. You can do a process of having a shared array buffer and then having web workers. And this has problems because of having shared memory. And I think you just sort of lack the context of a mutex inside of JavaScript.
It's possible to make a mutex in JavaScript.
Yeah. So it's been getting more support for actual actual multi-threading. Like WebAssembly supports that, but it's just not really like production ready yet. And I don't know. I guess the point there is that this kind of thing's still in its infancy in a lot of ways. Getting WebAssembly to be majorly efficient and performant is definitely like a newer area of work. Yes.
When you ran the EM++ compiler, did it look at C++ and actually compile it, or did it just look at it and generate Emscript virtual machine instructions?
Here it just did virtual instructions for, I mean, if that's essentially what Emscripten does, right? If you were wanting to like compile an executable, you can't extract it out of the Emscripten compile process somewhere along the way. and then get like a CPP executable and a WASM or something. Like it's for this stacked base virtual machine. It's what it's compiling for. So. Well, thanks for coming, everybody. Appreciate it.